Alright, in this video we're going to go over two methods that we use to find the velocity, angular velocity, acceleration, and angular acceleration of an object when it's undergoing rigid body motion in a plane, and then there's relationships between these quantities of the translational motion and the rotational motion. As an example, when we look at this window that is on a hydraulic cylinder, we can see that as it opens, of course, the angle that it makes with the vertical is going to change, but also the length of the piston from A to B is going to change as well. So if we want to know what the position of the rod is and how it relates to theta, we can then figure out the translational velocity of point B on the window related to the hydraulic cylinder, and also the angular velocity and angular acceleration of the window. All of these are going to be intertwined. Similarly, we can see that this linkage here, where the piston at point C is moving, is going to be related to the angular position and angular velocity of the piece AB, as well as the distance that A is from C as it moves back and forth. Again, we want to try to find those relationships. This is called, the procedure that we would go through for these things is called absolute motion analysis. And once you get the hang of it, it's really not that bad. Basically, we have some point that's undergoing some sort of rectilinear motion. That means it's moving in the xy plane, but we can also relate it to the angular velocity and the angular acceleration of a line that lies on the body. So what do? First, we find a point on the body, and we just label this like with a coordinate. Maybe we choose S, and that's going to be measured from some origin. Now, from this line, we're going to measure the angular position of a line lying on the body, and somehow we then can write a relationship between that position S and the angle. So S might be a function of the angle. Then, the way that we find a relationship between velocity and angular velocity is to take the time derivative of that expression, and you'll get a relationship between the linear velocity and the angular velocity. You can then take a second derivative to get the relationship between linear acceleration and angular acceleration. So that sounds all well and good, but it doesn't really make any sense unless we have an example that we could try to apply here. So here we have this link A to B, and notice it's rotating in the clockwise direction. So this is A to B, and notice that it's rotating in this direction, in a clockwise direction. And as it does that, this whole slot is going to be moving. This, as AB rotates, this is going to be moving back and forth. And so, in this question, what we're trying to do is we're going to say, okay, when this angle theta, this angle right here, is equal to 60 degrees, we're told that this is moving to the left with a velocity of 5 meters per second and an acceleration of 2 meters per second squared. And so we want to try to figure out, given that information, what is the angular velocity, omega, of AB, and the angular acceleration of AB. So how are we going to do that? So we're given a hint. Find the x-coordinate to be the distance between A and B. So what do they mean there? So here's point A, and here's point B, and so this is equal to x. And you can see that we could write x as a function of theta and the length of the link AB. So once we do that, that's the procedure that's outlined in our procedure that we just saw in the previous slide. So we designate this length x. We're going to write it in terms of theta then we're going to take the time derivatives to figure out how velocity and omega and acceleration and alpha are related to each other. So let's go where we have a little more. So here's our value x. Now if I look at that, I can see that this is also, here I'll do it like here. If I do this triangle, this is also x, and we could write x as 200 millimeters times the cosine of theta. Now I'm going to write that because our velocities and accelerations are given in meters. I'm going to rewrite this. I'm going to change it to 0.2 meters times the cosine of theta. Now we'll take the time derivative. X dot is equal to 0.2 minus, because we take the derivative of the cosine, we get minus the sine, times theta dot. Because we're taking the derivative with respect to time, so we need to do the chain rule. And so also we could write theta dot as omega. All right. Now our expression for x double dot is we're going to have to use the product rule and as well as the chain rule. So that's our first term. Oops, sorry. So just clean that up a little bit. You got minus 0.2 cosine of theta times omega squared minus 0.2 sine of theta times alpha. Okay, so we have those two expressions. Now we're going to use this expression and this expression and evaluate at theta equals 60, because at those values we know that v is equal to minus 5 meters per second and acceleration is equal to minus 2 meters per second squared, and that's because the negative signs are because they're going to the left. And just so you don't wonder, like, where did our negative signs go? Because they are in our expressions. So let's go to the next slide with a little more room. So we found that x dot could be written as minus 0.2 times the sine of theta times omega. So if we let this equal minus 5 equals minus 0.2 times sine of 60 degrees times omega, we get an omega of 28.9 radians per second. So we got that. Now we do the same thing with the acceleration. I'm just going to rewrite my term for acceleration. And now we said our acceleration when theta was equal to 60 was minus 2. And we also already know what omega is because we just found it previously. And so we can use that to solve for alpha. And alpha actually does turn out to be negative, about negative 471 radians per second squared. So we get that value. So that's an example of like what we're talking about. The idea is that, you know, you can sort of talk about a distance and express it in terms of an angle and then be able to get a relationship between velocities of something and those angular quantities. Now sometimes we have things that it's a little easier if you can sort of express the position of one point relative to another one, and then use the motion of that first point, that sort of central point, to be able to figure out the motion of the relative point. So we call this relative motion analysis. So here in this picture we have a slider block A, and it's moving horizontally to the left with this velocity. So right here it is. Now it's going to cause the link CB right here. It's going to cause this to rotate counterclockwise, and so as it does, the velocity of point B is going to be tangent to its path. So the idea is that this is kind of going around in a circle, and this velocity B is tangent to that circle. And so can we figure out some information about, say, what's the angular velocity of AB, and how can we relate that? So what are we doing here? Here's another example where we have some gears and they're all interrelated to it, and we want to be able to express their angular velocities relative to each other. So if we have some sort of combination of translation and rotation, what we do is we choose a base point. So for instance, here we have point A, and so notice here, this piece right here is sort of moving like this, but then a little bit time later, it's not only translated, but it's also rotated a little bit. And so we're trying to figure out, like, if we know motion of one point, like point A, can we figure out the motion of point B because it's attached to it? And so what we basically are saying is the displacement of point B is going to be related to the displacement of point A plus some displacement due to rotation. So the first term is just because the whole thing translated, so it moved, in the horizontal direction, but then also it rotated. Now we're going to use the result that we found in the last chapter, but again, here just another thing to think about is here, point A, we see it moving with some velocity, but there's also the bar AB is also rotating about point A. So thinking about that, as A moves and rotates, how are we going to talk about the motion of B? And again, we can use the relationship we found before and say that the velocity of B is equal to the velocity of A plus a term that is the motion of B relative to A. And that motion relative to A is due to rotation, and so we use a result that we found earlier in the chapter, that rotational velocity due to rotation, can be expressed as the angular velocity times the radius vector. And in this case, the velocity of B relative to A due to the rotation of that piece is equal to the angular rotation plus the position of B relative to A. So for instance, here we have this complicated motion, and we say, okay, so we know that in this link that goes from B to C, we have point C that's just sitting there, but we want to know, we have A that is moving back and forth, but then we also have B, which is actually able to rotate a little bit. So the velocity of A will help us find the velocity of B because it'll play a role, but then there's also B is rotating as well. And so we have this term to add to that motion of B. So basically it's the idea is if you know one of the points and then you can describe another point relative to it and its rotation, you can actually figure out how fast it's moving. So for instance here's a picture where A is moving to the left. Now B is sort of rotating. We know that it's rotating here because of the way that it's drawn. And we know that the velocity vector will be tangent to that rotational path or that circular path. And so that if we talk about the position of B relative to A, if we can express that, then the term of velocity of B is going to be, you add to the velocity of A this term of B relative to A. Another example of this would be a rolling wheel, is another time when we could do this. So here we have a wheel, and we have 2 points on the wheel, the point of the wheel that touches the ground and the center of the wheel. Now if we wanted to know, of course the wheel's rotating about its axis, if we wanted to know how fast is the center of the wheel moving, we would say, okay, we would take the velocity of point A plus the position of B relative to A, which would be given by this vector, and then we would take the term that would express that velocity due to the rotation would be omega cross with that vector. And so this becomes the case where we would want to be able to write each of these terms in a vector notation and then put them into the equations. Now here, one of the things that would be helpful to us is that we know that when we use this term, when we get an answer, VB is in the positive x direction. So if we get any other components, like if we end up with a calculation that gives us, say, a y component, we know that that has to be 0 because of the fact that that velocity of point B can only be horizontal. It is not going to be moving up and down. And sometimes using the fact that one of the components is equal to 0 can help us figure out what the other quantities are. For instance, if we don't know what omega is, that condition might allow us to find omega. So basically, going through the procedure that we would use for the relative velocity equation is, first we find our xy coordinate, and we're going to draw the picture of the diagram. And then we want to figure out what is the relative velocity vector for your point B relative to A, which is sort of like your anchor point. Then you use this equation to express V, the velocity of B relative to A, using the information that you're given, and use your components of that expression and your givens to be able to figure out any of your unknowns. For instance, as we saw in the last example with the wheel, the velocity had to be in the horizontal direction. Therefore, if we got any terms that were in the y direction or the vertical direction, we would know that those components would have to add up to be 0, and that might help us solve for an unknown quantity, say, for instance, the angular velocity. If our answers end up to be negative, that only means that our assumption for a particular direction was wrong, and then we know that the direction is in the opposite direction. All right, so I think that that's it for now. We'll do some examples in class, and I think that'll help put it in perspective, and it'll make more sense when we use this.